Hello friends, welcome back. In worked example 3, we computed the gradient of a scalar field in Cartesian coordinates. The formula was beautifully symmetric. Nabla f equals partial f partial x x hat plus partial f partial y y hat plus partial f partial z z hat. 3 partials, 3 unit vectors, no extra factors. Today we ask the natural follow-up. What does that formula look like in cylindrical and spherical coordinates? You might expect it to be the same recipe, just take 3 partials. It is almost that simple, but not quite. The cylindrical formula picks up a factor of 1 over rho in front of the phi term, and the spherical formula has both a 1 over r and a 1 over r sine theta. Where do those factors come from? The answer is the same in both cases, arc length. When you move a tiny angular step in Cartesian, you also move a distance dx. The coordinate and the distance are the same. But in cylindrical, a step of d phi in angle corresponds to a distance of rho times d phi along the arc. The bigger your radius, the longer the arc. So when the gradient asks for change per unit distance, we have to divide by rho to convert from change per unit angle. That is the 1 over rho. The same argument with rho replaced by r sine theta gives the spherical factor. Let's write the two formulas side by side. In cylindrical, nabla f equals partial f partial rho rho hat plus 1 over rho times partial f partial phi phi hat plus partial f partial z z hat. The rho and z partials look just like Cartesian, only the phi term carries the 1 over rho. In spherical, nabla f equals partial f partial r r hat plus 1 over r times partial f partial theta theta hat plus 1 over r sine theta times partial f partial phi phi hat. The r partial is naked, same as the rho partial in cylindrical. The theta term has a 1 over r, and the phi term has a 1 over r sine theta. 2 practical points before we use them. First, the underlying definition has not changed. df equals nabla f dot dl in any coordinate system. The factors come from how dl is expressed in each system. Second, you must always include the factors, even if it looks like they cancel. We will see in the first example that the 1 over rho explicitly contributes a numerical factor. Leaving it out would give a wrong answer. Worked example 1, cylindrical. Take f of rho phi z equals sine of 2 phi plus z. Our point is p equals 2 pi over 6, 1. We want the gradient at p. Step 1. Partial with respect to rho. Treat phi and z as constants. The function has no rho in it at all, so this derivative is simply 0. The rho component of the gradient is 0. Step 2. Partial with respect to phi. Now rho and z are the constants. The derivative of sine of 2 phi with respect to phi is 2 cosine of 2 phi. The derivative of z is 0. So partial f partial phi equals 2 cosine of 2 phi. Now apply the cylindrical recipe. The phi component of the gradient is 1 over rho times this partial. At p, rho equals 2, so we get 1/2 times 2 cosine of 2 times pi over 6. 2 times pi over 6 is pi over 3. Cosine of pi over 3 is 1/2. So we have 1/2 times 2 times 1/2, which equals 1/2. The phi component is 1/2. Notice this, the 1 over rho is not just decoration. It produced the 1/2 factor that ended up in the answer. Step 3. Partial with respect to z. Treat rho and phi as constants. Sine of 2 phi disappears, and the derivative of z is 1. The z component is 1. Putting it all together, nabla f at p equals 0 rho hat plus 1/2 phi hat plus 1 z hat. The magnitude is the square root of 0 plus 1/4 plus 1, that is square root of 5/4, which is square root of 5 divided by 2, about 1.118. Worked example 2, spherical. Take f of r theta phi equals r times cosine of theta. Our point is p equals 2 pi over 3 pi over 4. Before we compute, recognize this function. In spherical coordinates, z equals r cosine theta, so f is just z dressed up in spherical clothing. We already know that the gradient of z is z hat. After applying the spherical formula and the unit vector identity, we should land back at z hat. This is our sanity check at the end. Step 1. Partial with respect to r. Treat theta and phi as constants. The derivative of r cosine theta with respect to r is cosine theta. At theta equals pi over 3, cosine of pi over 3 equals 1/2. The r component is 1/2. Step 2. Partial with respect to theta. Treat r and phi as constants. The derivative of r cosine theta with respect to theta is minus r sine theta. The theta component of the gradient is 1 over r times this, which gives minus sine theta. At theta equals pi over 3, sine equals root 3 over 2. So the theta component is minus root 3 over 2. Notice that the 1 over r exactly canceled the r in the derivative, but you still must write the 1 over r in the formula. If we had a function with extra r dependence, the cancellation would not happen. Step 3. Partial with respect to phi. The function has no phi in it. The phi component is 0. Putting it all together, nabla f at p equals 1/2 r hat minus root 3 over 2 theta hat plus 0 phi hat. The magnitude is the square root of 1/4 plus 3/4 plus 0, which equals 1. Sanity check time. We claimed nabla f equals z hat. To verify, expand z hat in spherical unit vectors. The standard identity says z hat equals cosine theta r hat minus sine theta theta hat. At theta equals pi over 3, that is 1/2 r hat minus root 3 over 2 theta hat. Exactly what we got. Quick recap. In cylindrical, nabla f equals partial f partial rho hat plus 1 over rho times partial f partial phi hat plus partial f partial z hat. In spherical, nabla f equals partial f partial r hat plus 1 over r times partial f partial theta hat plus 1 over r sine theta times partial f partial phi hat. The factors of 1 over rho and 1 over r sine theta are not decoration. They convert change per unit angle into change per unit distance because angular displacement in these systems covers an arc length proportional to the radius. In the next worked example, we will introduce divergence, the second differential operator, and compute it on a vector field. See you then.